This is Chapter 16, Basic Transformer Characteristics. Mutual inductance, this is the property of inducing voltage in one circuit by varying the current in another circuit. So there's two separate currents. They both have inductors in them. One of them has a source driving the circuit, and it's an AC source, and as the circuit has its current passing through it, it flows in one direction, then the other, and so the magnetic field grows and collapses and reverses polarity and collapses again. That process is repeated, and that growing and collapsing magnetic field is cutting the inductor of the neighboring field, which in turn induces a voltage and current in that secondary circuit. So the transfer of energy is by the magnetic linkage between the two circuits. Mutual inductance is measured in henries, just like inductance is, and the symbol for mutual inductance is M, as opposed to L, which stands for inductance. This is a simple circuit. This is the idea of a transformer and how it might work. And so we have a source in circuit A, driving current, alternating current back and forth, back and forth. And so the magnetic field is growing and collapsing, growing in the opposite direction and collapsing. And as that field grows and collapses, it's cutting this neighboring inductor in a secondary circuit. And so the two circuits are not linked electrically, rather they're linked by magnetic field. I should also point out that this only works in an AC circuit. If this were a DC circuit, when the current flows in one direction, the magnetic field would grow, and then that's it. Right? The magnetic field then would be stationary until we turn the circuit off, and then the magnetic field might collapse. So with an AC circuit, we have the growing and collapsing magnetic field, and that is necessary for a transformer to operate. This is an example of the coefficient of coupling, and so you can see that if the two circuits are far apart, the magnetic field is limited in the space that it occupies, and so if the two inductors are far apart, there's very little linkage between the magnetic fields. But if the two circuits are physically close, the magnetic field, many more lines of that field are cutting the neighboring circuit. And so we have a low coefficient of coupling here on the left, and we have a high coefficient of coupling here on the right. Coefficient of coupling is a percentage. Often we need to express that as a decimal rather than a percentage for calculations. These are several examples of what affects the coefficient of coupling. First of all, is proximity. That's what we just talked about. Close inductors have a higher coefficient of coupling than inductors that are far apart. The way the inductors are aligned is going to affect the coefficient of coupling. When the two inductors are parallel to one another, we will have the highest possible coefficient of coupling, whereas when they're parallel to one another, the coupling will be zero, and no voltage or current will be induced in the secondary in this situation. Here, as the field grows and it's cutting the windings, it's cutting each winding essentially in both directions. At the top, let's say it's out of the page, and at the bottom it's into the page, so the direction of the windings is different. And as the magnetic field cuts those two windings and their orientation is different, they're going to induce voltages that are opposing each other, and so they'll cancel each other out, and there will be no induced voltage in the secondary. We also have the core material. Core materials like iron, they have lower reluctance, and the magnetic field exists in them more readily than just an air core, and so iron core transformers will have a higher coefficient of coupling, as opposed to air cores, which will have a relatively low coefficient of coupling. So transformer, this is a component for electrical circuits that transfers energy between circuits by the electromagnetic induction. Typically it has a primary and at least one secondary winding, though it could have more. It could have multiple primary windings and multiple secondary windings. Usually it's one primary and one secondary, maybe one primary and two secondaries. These are some terms associated with transformers. The primary, that is the circuit that contains the inductor that is being driven by a source. We call that the input. It's usually a single winding. The secondary is the other circuit that is having voltage and current induced in it by the primary. That'll be the output. That is where we attach the load. And the secondary oftentimes has multiple taps, though it doesn't have to. So these are some examples of different transformer layouts. We're going to typically have one source and one load, one primary winding, one primary source circuit, and a secondary load circuit, and they usually have a core. We could have a single primary winding and two secondary windings all in the same core. We could have a primary winding with a secondary winding that has multiple taps, and so this is all one continuous piece of copper wire that makes up the winding, but at various locations the insulation from the wire is removed and we attach another wire there, and so we call that a secondary tap. This is essentially like having multiple inductors in series with one another. When we have inductors in series, they divide the voltage the same way that resistors do. A lot of transformers have just a single center tap, and so the voltage from the center tap to one of the main leads is half as what it is from the main lead to the other main lead. So the center tap voltage is usually half of the full secondary voltage. Transformers usually have sense dots on them, and this has to do with the direction that the windings are wound. So for example, if both windings are wrapped, let's say clockwise, if you were looking down from the top, when the current flows through the primary and the magnetic field grows, it induces a current in the secondary that causes current to flow in the same direction. If the secondary winding was, let's say, wound counterclockwise, where the primary was wound clockwise, we might see currents flowing in the opposite direction. So current might be flowing in through the primary in one direction and out through the secondary in the other direction. And so the sense dots indicate to us the polarity of each winding. Transformers that have no core, this would be the schematic symbol for a transformer with an air core. Iron core transformers, this is the schematic symbol. And we can draw schematic symbols to represent transformers that have a single primary with a core with multiple windings, and some of those windings can be center tapped. So we would draw the schematic symbol as to whatever is appropriate for the actual transformer. The core material can be air or iron or powdered iron. Air, of course, is going to be the least effective. Powdered iron would be the most effective. Mutual inductance, we've talked about this already, but mutual inductance is the ability of one inductor to induce voltage and current in another inductor. And so the mutual inductance depends on the inductance of the two inductors. And so a transformer is two coils, a primary and a secondary, and each coil has its own inductance. And the coefficient of coupling is also going to affect the mutual inductance. So we can calculate mutual inductance if we know the coefficient of coupling and the inductance of each individual winding that makes up the transformer. We find the product of the inductances, take the square root, and then multiply it by the coefficient of coupling. Coefficient of coupling for a transformer is generally assumed to be 1. They're constructed in such a way that we want K to be as high as possible. We can have two transformers in a circuit, we can have two inductors in a circuit that are not necessarily a transformer. There's just two inductors in a circuit, they're in series. And we can still have mutual inductance between the two though. When current is flowing through the circuit, the two inductors, let's say, are in series. Each of them has a magnetic field growing around them, and if the inductors are in close proximity to each other physically in the circuit, when the magnetic field grows around one inductor, it induces a voltage in the second. And so we can calculate the total inductance. Up until now we've just added them if they're in series, but in reality we need to consider the mutual inductance. And so two coils can be in a circuit together, they can be in series, and when the magnetic field grows around one, it cuts the other, and it aids the flow of current through that inductor. That's one possibility. We'll call that series aiding. It's possible to have two inductors in a circuit where when the magnetic field around one grows, it cuts the secondary inductor or the second inductor in the circuit, and that induces a voltage that opposes the flow of current in that inductor, and we'll call that series opposing. And so the way we really calculate total inductance is to add the inductances. That's how we did it before. But we also need to add in 2 times the mutual inductance. And again, the mutual inductance we calculated using this formula. So if the two inductors are opposing one another, the mutual inductance will be subtracted. So when we find total inductance of a circuit, we will add the inductances together, and then we'll subtract 2 times the mutual inductance. It's possible for inductors to be in parallel and aid each other. And if they are, we will find the total inductance still by summing the reciprocals and then taking the reciprocal of that sum. but we must add mutual inductance to each inductor before we take the reciprocals, and then we'll add them and then we'll take the reciprocal. It's possible for inductors to be in a parallel circuit that oppose one another, and so here we will subtract the mutual inductance from each inductor, then take the reciprocal, add them together, and take the reciprocal again. Transformer concepts: no load on the secondary. If there is no load on the secondary, the primary acts as a single inductor. So if the secondary circuit is left open and there's no load, the primary circuit operates just as if the secondary is not even there. There's no interaction between the magnetic fields from the secondary to the primary. Current flow in the primary depends on the applied voltage and the induced reactance, and so we know that current is voltage divided by resistance, or in the case of inductors, it's voltage divided by reactance. And so the amount of current that is flowing is going to depend on the applied voltage and the inductive reactance, or in other words, the impedance. Primary current produces a magnetic field which cuts the primary and the secondary, and so that's how inductors work. That's what we've talked about in the past, where the current in an inductor does not grow instantaneously. It grows at a slower rate than instantaneous. That's because the magnetic field growing around an inductor is actually cutting its own windings and opposing the current flow in that inductor itself. And so a counter EMF is produced in the primary, just like with any other inductor. Voltage is produced in each turn of the secondary when it's linked by the magnetic flux from the primary to the secondary. And so transformers can be either step up or step down. They generally share an iron core, and we have a primary winding and we have a secondary winding. In order to get a step-up winding, we need fewer turns on the primary than we have on the secondary. And so when current flows through the primary, a magnetic field is induced. The flux lines want to exist in this iron core, so the flux lines leave the primary coil and they want to jump into the core material, the iron. And so as they're doing that, they're going to be cutting all of the windings of the secondary. And since there's more windings in the secondary, the flux that is cutting the secondary is going to induce a larger voltage because there are more windings here. And so that'll be a step-up transformer. We can apply low voltage to the primary, and we'll expect a higher voltage out at the secondary. The same thing works for step down. Here we will have more turns on the primary but fewer turns on the secondary. And so again, when the flux lines grow and they try to exist in the iron core, they have to cut the windings of the secondary to do that. Fewer turns on the secondary means less voltage being induced, and so we can apply a high voltage to the primary and get a low voltage out at the secondary. So this brings us to the turns ratio. The turns ratio is defined as being the number of turns in the primary coil divided by the number of turns in the secondary coil, and that will give us the turns ratio. The voltage applied to the primary is related to the voltage induced in the secondary by the turns ratio. They're actually equal. And so if you know the number of turns in the primary and the number of turns in the secondary, and you knew the voltage in the primary, you could calculate the voltage in the secondary. So the voltage ratio must be equal to the turns ratio. This is an example where we have a transformer with 250 turns on the primary and 1,000 turns on the secondary. And so the turns ratio from primary to secondary would be 1 to 4. So this fraction of 250 over 1,000 reduces to 1 over 4. We could also express the turns ratio as secondary to primary, though that's not as common. But the ratio of 1,000 over 250 reduces to 4 to 1. In this example, we see a transformer where they share an iron core. And so as current is flowing through the primary, the magnetic field is growing. And as it grows out and it's trying to stay in the iron core, as it grows out to be a loop within the iron core, it's cutting the secondary. And so in this example, we see 240 volts being applied to the primary, and we are presumably measuring 120 volts out at the secondary. And so you can see that this is a 2 to 1 ratio for the voltage. The input voltage is twice that of the output. And so that means that the turns ratio must be 2 to 1 as well, because the voltage and the turns ratios are equal. And so in this example, we see 300 turns on the primary and 150 turns on the secondary. So the turns ratio is 2 to 1. So the turns ratio is equal to the voltage ratio. 3 over 150 reduces to 2 over 1, just as 240 over 120, which is the voltages, also reduces to 2 over 1. And we could take the reciprocals of these, have secondary to primary rather than primary to secondary, but either way they will still give us equal ratios. The current ratio for a transformer, however, is the reciprocal of the turns ratio. So transformers transfer power, but they do not create power. So we're applying power to the primary, a voltage and a current, and we can get a power from that, and it's transferring that power to the secondary. So the secondary's power is not being created, rather it's being transferred from the primary to the secondary. And so it's not possible to create or destroy energy. So the power supplied to the primary must be equal to the power being used by the secondary, and therefore the voltage times current for the primary must be equal to the voltage times the current for the secondary. In other words, the powers must be equal. What that all means is that the current ratio is secondary current divided by primary current will be equal to the primary turns divided by the secondary turns. So with voltage, it's primary to primary and secondary to secondary, but with current, it's primary to secondary and secondary to primary. Here we have an example where the primary circuit has an AC source. The voltage being applied is 100 volts. The current that's flowing in the primary is 400 milliamps, and therefore the power is 40 watts, right? Voltage times current gives us the power. So we have 40 watts in the secondary. That means we must have 40 watts in the secondary as well, right? So we can't destroy or create the power. And so if we are stepping the voltage down to 20 volts, that means that the current must be stepped up to 2 amps, so that when we multiply voltage times current, we still get 40 watts. No matter what happens, the power in the primary must be equal to or greater than, the primary power must be greater than the secondary power. And that's because the transformer is not 100% efficient. There's always going to be some energy loss due to heat or other factors that we'll explore a few of those here in just a few minutes. The impedance ratio, and I'll prove this for you here a little bit later, but the impedance ratio is the square of the turns ratio is equal to the impedance ratio. And I'll prove this to you as to why it's the square in just a moment. But it is still a direct ratio. That we have secondary turns over primary turns is equal to secondary impedance over primary impedance. So we have secondary to secondary and primary to primary, except it's squared for the impedance. In this example, we have a primary circuit with a primary coil, and they're sharing a core material with a secondary circuit, and the impedance of the load is 8 ohms. And we know, or we're being told, that the turns ratio is 4 to 1, that's primary to secondary, or 1 to 4, that's secondary to primary. And so we're being tasked with calculating the primary impedance here. This is what we're not supposed to know yet, 128. So we know that the secondary resistance is 8 ohms, and the primary impedance is what we're solving for. So the secondary impedance is 8 ohms. The turns ratio, primary to secondary, is 4 over 1, which is just 4. And so the turns ratio is 4. And so the formula says that we square the turns ratio, multiply by the secondary impedance, and that gives us the primary impedance. So 4 squared is 16. 16 times 8 is 128. We expect a primary impedance of 128 ohms. Now the transformer is not 100% efficient. There are losses due to the copper. And so the copper that makes up the windings does have resistance, and so we can calculate the power lost to the resistance of the copper windings by using P equals I squared R, where R is the resistance of the coil and I is the current passing in through the coil. We also have core losses. This is where the core itself is being cut by the magnetic field. When the magnetic field cuts the core, it induces current in the core. And so the core is also using some power because it has current flowing in it. We call those eddy currents. We also have hysteresis losses. This has to do with the magnetizing of the core and then trying to reverse that magnetization. And so some energy is being lost when we reverse that magnetization. The efficiency of a transformer, just like any type of efficiency, is always calculated by P out divided by P in and then times 100%. So the efficiency is the ratio of the output power, or the secondary power, divided by the input power, or the primary power. times 100%, the input power will always be more or greater than the output power, and so we're always going to get an efficiency that's less than 100%. This is showing us how a couple of different transformers are constructed. We can either have a core type transformer, where you can see that we have windings on a core that's sort of like a loop, or we can have the shell type transformer, where you can see the core material is like a double loop, and then the windings are wrapped around this inner part of the core here. There are several different types of transformers. The most common one is the power transformer. It's heavy because it uses an iron core, so transformers tend to be heavy. They may be large, like what you see outside of your house on the telephone pole. You probably have a transformer on your pole outside. Or they can be small. We can have these in electronic devices. We can have smaller transformers to step up or step down, or even to isolate circuits. They usually use a laminated iron core. This helps to reduce those eddy currents, the current that is induced by the growing and collapsing magnetic field in the core material. Laminating the iron core helps to reduce the amount of current that flows in them. And so by laminated, we mean that there are several thin layers of iron put together with insulation in between them. And so the magnetic field exists there still easily, but the currents that are induced there are not as easily induced. Power transformers also have a short flux path. So with a power transformer, our goal is to transfer as much power from the primary to the secondary as we can. We want the efficiency to be as close to 100% as we can, and so that requires a short flux path. The core shapes can either be core or shell, and there's usually one or more primary and secondary windings. We may have only one winding that is tapped, such as an auto transformer. So all of the transformers we've seen so far has a primary and a secondary winding, though it's possible to have a transformer that only has one winding, and that one winding acts as the primary and the secondary, and we'll see some examples of that here as we go. Power transformers can be used to isolate circuits. We can have a circuit with a high voltage and a low current at the primary, but we want a high voltage and a low current on the secondary, and those two circuits are completely isolated from one another. They are not connected electrically, rather they're connected by a magnetic field. Power transformers, though, cannot be used at high frequencies. The higher the frequency is, the faster the magnetic field has to grow and collapse, and the more quickly we need to demagnetize the core material and remagnetize it with the opposite polarity. The inductors also resist the change in current, and so if the frequency is high and the current is trying to change rapidly from one value to the other or from one polarity to the other, the inductors inherently resist those changes, and so these power transformers will not work at high frequencies. Here we see some examples of a power transformer. The one on the right here is more common, where we have a single winding. This acts as the primary and the secondary, and the windings are bare, but they're separated by air, so the wires can't touch each other, otherwise we would have shorts. And the primary voltage is applied to the full winding, and the secondary is taken out from the winding by use of a wiper. And so the wiper makes contact with the winding at some point. That essentially divides the winding into two separate windings, like two separate inductors. And we know that the voltage, when we have two inductors in series, the voltage is divided between them proportionally to their inductance. And so the output voltage would be, in this example, maybe 50%, because the wiper is at about halfway through the inductor. This configuration is a little bit less common. This is a step-up power transformer that only uses one winding. Here the AC in is the wiper, where we can adjust where the voltage is being applied to the coil, and if we apply it to the full coil, the AC out would be 100% of whatever the AC in is, but if the wiper is somewhere down like 50%, then the output AC would actually be double that of the input voltage. This is a flow chart that shows us a possible system using what we call a variac or an auto transformer. So we have an AC source, which would be like the outlet that you have in your home, and a power cord will plug in to the source, and we have an isolation transformer. This is a transformer to separate the AC source electrically from the variac or the auto transformer. So this transformer may have a 1-to-1 ratio. Its only purpose is to stop, say, voltage spikes coming from the power company from bleeding through into our variac and into our load, and so an isolation transformer can accomplish that. The variac is a type of transformer that only has one winding and a knob that you turn. When you turn the knob, you're adjusting the wiper along the coil, and so the output voltage is variable depending on where you set the knob to be. So the variac plugs into the isolation transformer, and then the load plugs into the variac. We also have audio transformers for things like stereos. They're smaller, they're lighter, they're unable to operate at frequencies above the audio range without losses, so we're still limited by the frequencies that we can apply to these. Isolation transformers, they're a safety device used only to prevent severe electrical shock or worse. They are used to keep two separate circuits electrically separate from one another, but the circuits are linked still by magnetic field, so voltage spikes in the primary do not bleed through into the secondary. Radio frequency transformers, they use an air core or a powdered iron core, and that's used to reduce the core losses. That helps with the eddy currents. And they have low inductance values. Radio frequency transformers are typically smaller. These are the types of things that you would find in an antenna in your car that picks up the radio station and then steps that power up or down to be amplified by the stereo. This is an example of a toroidal coil form of a transformer. You can see here this is actually called a current transformer, so it looks like a donut. The windings form a donut around this core material, and the way this works is if there's a single wire that passes right through the middle of this coil, and that wire is carrying AC current, as the current flows back and forth through that single wire, a magnetic field grows and collapses, and it's cutting all of these windings, and so we can step that current up or down through the leads of this transformer. So this is called a current transformer. This is just an example of a type of coil that uses a heavy wire, and you can see that there's no insulation on this wire. This is what you might find inside of a variac, and so it has few turns of heavy gauge wire to handle high current, and they're separated by this strip here. You can see this is an insulation material. It keeps all of the turns of the coil separate from one another, so there's no insulation on this wire. This is some tips on how you can troubleshoot transformers. If you have an open winding like this, where the wire has been broken and it's not supposed to be broken, you can test that by measuring the resistance. If you measure the resistance and the resistance is infinite, you know that means you have a break somewhere in that winding. If you think that you might have a short, when you measure the resistance, you'll measure 0 ohms, so there are very low ohms, and so there should be some resistance in all of the turns that make up the transformer. If we have a short in the transformer, that resistance will be less than it should be. It's possible to have a short between the primary and the secondary, so when we measure the resistance from a lead on the primary to a lead on the secondary, we should measure infinite ohms. They should not be connected electrically, but if there's a short there, then they are connected. And so the resistance in the primary and the resistance in the secondary measures to be normal, but the resistance from the primary to the secondary would be 0 ohms if there was a short. That should be infinite. It's possible to have a short to the core material where the insulation has burned or worn off of the windings that make up the primary or the secondary. If you measure the resistance from one of the leads of the windings to the actual core material, that should be infinite resistance, and if the resistance is low, you know you have a problem. So this is a type of circuit that we can use to test a transformer. Here we see the transformer in the middle, and if we apply power to the primary transformer, like plugging it into an outlet, and we put a light bulb in series with the transformer, and there's no load connected, the secondary is open, if the lamp glows dimly or not at all, there are no shorts. So when the secondary is open, we expect there to be very little to no current in the primary as well, and we'll talk about that later. But the lamp should not glow very brightly at all, because the current should be essentially non-existent in the primary if there's no current able to flow in the secondary either. So if the lamp glows brightly, however, that means we have a short. So there should be no current in the primary if we're not allowing current to flow in the secondary by leaving it open. Let's look at some of the formulas we have for transformers. The primary voltage divided by the secondary voltage is equal to the number of turns in the primary divided by the number of turns in the secondary. And let's also say that the power consumed by the primary must be equal to the power consumed by the secondary. And the power on the primary is the primary voltage times the primary current. That's the formula for power. And the secondary power is the secondary voltage times the secondary current. Now, if I divide both sides by Vs, I'll get Vp IP over Vs. Over here, when I divide by Vs, it cancels. We get Is. And then if I divide both sides by IP, we get Vp over Vs equals Is over IP. And since Vp over Vs is equal to Is over IP, then Vp over Vs must also be equal to Is over IP. And so this shows that the turns ratio has sort of a cross relationship to current, whereas it has more of a direct relationship to voltage. Now let's look at this formula again. The power in the primary has to equal the power in the secondary. So Vp IP equals Vs Is. Now this time I'm going to divide both sides by IP, but I'm not going to cancel these. Instead, I want to say that Vp over IP is the primary's impedance, right? So voltage divided by current is impedance, and I still have this IP here. Then I want to divide both sides of the equation by Is. And again, I don't want to cancel the Is's. Instead, I want to say that Vs over Is is the secondary's impedance. So we get primary impedance times IP over Is is equal to the secondary impedance times Is over IP. And now I want to divide both sides by the secondary impedance. These will cancel. And we get Zp over Zs times IP over Is is equal to Is over IP. And now I want to multiply by Is over IP on both sides, so that here on the left IP cancels, Is cancels, and over here we're going to get Is squared over IP squared. So the primary impedance over the secondary impedance will be equal to the secondary current squared divided by the primary current squared. And anytime you square the numerator of a square the numerator and the denominator of a fraction, that's the same thing as squaring the whole fraction. And Is over IP is the turns ratio, NP over NS. So what we get is Zp over, oh I'm sorry, that's Zs, Zp over Zs. We get Zp over Zs is equal to Is over IP is the turns ratio, NP over NS squared. And so this is the formula that we have that says that the impedance ratio is equal to the square of the turns ratio, and this is how we derive that formula. So we have these two formulas. The turns ratio is equal to the voltage ratio, the turns ratio is equal to the reciprocal of the current ratio, and the square of the turns ratio is equal to the impedance ratio. And so these are the three equations that we'll need to solve circuits with transformers in them. In this example, we have a transformer with a primary voltage of 300 volts. On the secondary, we know that we have 500 turns on the secondary. We have 25 ohms resistance, which is the impedance because that's the total impedance of the circuit. And we also have 3 amps flowing through the circuit. And we want to find out how many turns are on the primary, what is the current in the primary, and what is the impedance in the primary. And so we have a few formulas to use. First of all, well, obviously we have Ohm's law, which says that V is equal to I times R. We also have that the turns ratio is equal to the voltage ratio, and that is equal to the reciprocal of the current ratio. We also know that the turns ratio squared is equal to the impedance ratio. So these are the formulas that we'll need to solve these types of circuits. First thing I want to do is find out what the voltage is over here. Find out what the voltage is. So the voltage on the secondary will be equal to 25 ohms times 3 amps. And so we're going to have 75 volts. 75 volts. And we can use that information now to find out what the turns ratio is. So I don't know the number of turns on the primary, but I do know the number of turns on the secondary is 500. The primary voltage is 300 volts. Secondary voltage is 75 volts. We'll multiply both sides by 500 so that they cancel over here. And we can say that the number of turns on the primary is 300 volts times 500 divided by 75 volts. And so the number of turns on the primary is 300 volts times 500 turns divided by 75 volts, and we get 2,000. There must be 2,000 turns in the primary. So now we know the turns ratio. The primary to secondary ratio is 2,000 turns to 500 turns. These zeros cancel. We get 20 over 5, which is 4. Our ratio is 4 to 1. Now that we know the turns ratio, we can use that to find the current in the primary. So the primary turns to secondary turns is 4 to 1. And that will be equal to the secondary current, which is 3 amps, divided by the primary current, which we don't know yet. That's what we're looking for. And so we can cross multiply here, cross multiply. And so we will get, I'll start back over here, we'll get 4IP is equal to 3 amps. Right, so 4 times IP is 4IP, and 1 times 3 amps is 3 amps. Now we divide by 4. These cancel. And we can say that IP is equal to 3 amps over 4, which is 0.75 amps, 3/4 of an amp. And so that is the current in the primary. Now I should be able to find the impedance here by dividing the voltage by the current. And so I'll go ahead and do that. The voltage is 300 volts. We'll divide by the current, 0.75, and we get 400 ohms. Impedance over here should be 400 ohms. We also could have used this formula, and so the turns ratio is 4 over 1, or just 4. That gets squared. And this should be equal to the primary impedance, which I'm going to check and see if I get the same answer, divided by the secondary impedance, 25 ohms. So the primary impedance should be 16 times 25 ohms, and 16 times 25 is 400. So you see I got the same answer. And so now we've solved for all of the information, 2,000 turns over here, and now we've solved the circuit. In this example we have a transformer circuit where we have 150 turns in the primary with 100 volts AC. On the secondary we have 300 turns and we have 10 kiloohms of impedance. And so we'll start by finding the voltage in the secondary. So the turns ratio is equal to the voltage ratio. And so the turns ratio is 150 to 300. The primary voltage is 100 volts, and we're looking for the secondary voltage. 150 divided by 300 reduces to 1/2. We will cross multiply, and so we get Vs equals 200 volts, and that is the answer. Vs is 200 volts. So the secondary voltage is 200 volts. Now that we know the secondary voltage, we can find the secondary current just by using Ohm's law. 200 volts divided by 10 kiloohms. And so 200 volts divided by 10 kiloohms is 20 milliamps. 20 milliamps. Current here is 20 milliamps. Now that I know the secondary current, I can find the primary current using the turns ratio. NP over NS is equal to IS over IP. I'm looking for IP. So the turns ratio is 1/2. Secondary current is 20 milliamps. We're looking for IP, and so we'll cross multiply. We'll get IP is equal to 40 milliamps. So the primary current is 40 milliamps. And now that I know the voltage and the current here, we can find the primary's impedance, which will be the voltage divided by the current. So we'll have 100 volts divided by 40 milliamps. And so the primary impedance is 100 volts divided by 40 milliamps, which is 2.5 kilo ohms. 2.5 kilo ohms. Okay, and we can check some of our answers by saying that the power in the primary is the primary voltage times the primary current, which is 100 volts times 40 milliamps, which is going to be 4 watts. And then we can also check the power in the secondary, which is 200 volts times 20 milliamps, and we still get 4 watts. So that's good. If the powers are equal, that's a good sign that we've got the answers correct. I could also check my impedance ratio, make sure that my impedance ratio is equal to the turns ratio squared. We could certainly do that to check our answers. So let's say the impedance ratio is 2.5 kilo ohms to 10 kilo ohms. And this should be equal to the turns ratio squared. So the turns ratio is 1/2, that's squared. And so 2.5 kilo ohms divided by 10, the kilo ohms cancel. And so 2.5 divided by 10 is 0.25. And 1/2 squared is 1/4, which is also 0.25. So I'm just checking the answers here. In this example, we have a transformer circuit where the primary voltage is 50 volts. The secondary voltage is 285 volts. This is a step-up transformer. The voltage is higher at the primary, and so this is a voltmeter. We're measuring that voltage. Now, we can say that the primary turns to the secondary turns is equal to the primary voltage divided by the secondary voltage. Now, I know the primary and secondary voltage. They are 50 volts and 285 volts. And we generally want the turns ratio to be expressed as a fraction. So I'd like to try to reduce these fractions. Volts cancels. I could maybe start by dividing both of them by 5. And so NP over NS is equal to 10 over 57. And I don't believe that's going to reduce anymore. And so this is just an example of a circuit where this is all we can solve for. I don't know how many turns are actually in the primary. I don't know how many turns are actually in the secondary. I just know that the ratio is 10 to 57. For every 10 turns there are in the primary, there are 57 turns in the secondary. I don't have enough information to find the current or the impedance. In this example, we have a transformer circuit that has 300 turns in the primary with 120 volts source voltage. The secondary has 400 turns, and the load is 40 kilo ohms. And so we can start by finding the turns ratio. Turns ratio NP over NS is equal to 300 over 400. Zeros cancel. And the turns ratio is 3 to 4. So for every 3 turns in the primary, we have 4 turns in the secondary. Now we can use that information to find the voltage on the secondary. So the primary and secondary voltage ratio is equal to the turns ratio. Primary voltage, we have 120 volts. We're looking for the secondary voltage, and the turns ratio is 3 to 4. So we'll cross multiply. We get 480 volts is equal to 3 Vs. Divide both sides by 3. We get 160 volts is equal to Vs. So the secondary voltage is 160 volts. Now we can find the current in the secondary. Current in the secondary is 160 volts divided by 40 kilo ohms. The zeros here will cancel. 16 divided by 4 is 4. But let's make sure that I get the prefix right. We have 16 divided by 4 kilo. We've got 4 milliamps. 4 milliamps. Secondary current is 4 milliamps. Now that I know the secondary current, I can find the primary current. I know that the turns ratio is equal to the reciprocal of the current ratio. And so the turns ratio we already have as 3/4. Secondary current is 4 milliamps. Primary current is what we're looking for. We'll cross multiply. We get 16 milliamps is equal to 3 IP. Divide both sides by 3. And we're going to get 5.333, I think. Let's see. We've got 16 milliamps divided by 3, which is 5.333. So the primary current is 5.333 milliamps. Now we can find the primary impedance. Primary impedance will be the voltage divided by the current. Primary impedance is 120 volts divided by 5.333 milliamps. So the primary impedance is 120 divided by 5.333 milli, and we get 22.5 kilo ohms. 22.5 kilo ohms. And we could check our answers. The impedance ratio should be equal to the square of the turns ratio. Turns ratio again is 3/4. So the primary impedance is 22.5 kilo ohms. Secondary is 40 kilo ohms. This should be equal to the turns ratio 3/4 squared. And so we'll check our answers here. We've got kilo ohms cancels. We've got 22.5 divided by 40. So over here we have 0.5625. Over here we'll have 9/16, 9/16. And 9/16 is 0.5625. So these are equal. That just shows us that we have the correct answers. This will be our last example. This time we have a transformer circuit that has a turn ratio of 4:16. That reduces to 1:4. And 10 milliamps in the secondary, 25 kilo ohms in the secondary. And that's all we know so far. So let's start by finding the voltage here in the secondary. The voltage will be equal to the current times the resistance, or the impedance, which would be 10 milliamps times 25 kilo ohms. The voltage will be 250 volts. The voltage here is 250 volts. And now that we know the voltage and we know the turns ratio, we can start to find the information about the primary. So the primary voltage to the secondary voltage is equal to the turn ratio, primary over secondary. Turn ratio is 1:4. Make sure that the first number is the primary, that's the numerator. The second number is the denominator. Secondary voltage is 250. So we're looking for the primary voltage over 250 volts is equal to 1/4. We will cross multiply. We get 4 VP is equal to 250 volts. Divide by 4 on both sides. And we get VP is equal to, let's make sure. 250 divided by 4 is 62.5. 62.5 volts. So we get 62.5 volts over here. Now we can find the current. The reciprocal of the current ratio, secondary over primary, is equal to the turns ratio. Oops, I was supposed to say S there. So the secondary current I know is 10 milliamps. We're looking for the primary current. And the turns ratio is still 1:4. We'll cross multiply and divide. We get IP is equal to 40 milliamps. And so that'll be the primary current, 40 milliamps. Finally, we can find the impedance. So the impedance ratio, ZP over ZS, is equal to the square of the turns ratio. Turns ratio is still 1/4. secondary impedance is 25 kiloohms. So ZP over 25 kiloohms is equal to 1/4 squared. And so 1/4 squared is 1/16. We will multiply both sides by 25 kiloohms. So ZP is equal to 25 kiloohms divided by 16. And the primary impedance will be 25 kilo divided by 16, which is 1.563 kiloohms. 1.563. And so the primary impedance is 1.563 kiloohms. And so we can check our answer. If we multiply the current times the resistance, we should get the voltage. So we think that 62.5 volts should be equal to 40 milliamps times 1.563 kiloohms. So we'll multiply. 40 milliamps times 1.563 kiloohms is equal to 62.52 volts. So 62.5 volts is equal to 62.52 volts. A little bit of rounding error, but that helps us to see that we have the correct answers.